Okay. I think this is going to work now. If anyone watched the recording from the day before yesterday, basically any time since I redid this setup, you probably noticed that it was a black screen with this in the corner because they didn't realize what it was recording. So you got my voice and nothing. So I apologize for that. I did try to fix it before the end of the day yesterday, okay? But now hopefully it's working a little bit better. Okay? So what we are working on today, guys, we're going to just quickly review the work energy theorem stuff and then get into some problem solving kind of to do with that. Okay? So first off, okay, the big thing about work energy theorem is that work is a change in energy. Okay, a change in mechanical energy specifically. All right. In Science 10, that's going to mean a change in either potential energy or kinetic energy, but not both. Okay. In the truest sense, work energy theorem is a change in mechanical energy, which means it could be both. And in Physics 20, we do work energy theorem with both types of energy changing. But in Science 10, either potential or kinetic is going to change. So an example of doing work, okay, where potential energy is changing could be as simple as picking something up off the floor and then putting it on a table. Okay? Did I change the potential energy of that cup? If I pick it up from the floor and put it on the table. Okay, so does that mean I did work then? Okay. So that would be one example of a work energy theorem question. So I would have, in that case, that the work being done is changing the potential energy of the cup. Okay? Now, anytime we see the triangle, delta, okay, it means change. And that means final minus initial. So the work that I did in picking that cup up and putting it on the table is this. The work equals the final potential energy minus the initial potential energy. Can you guys read that, or do you use different color? Is it okay? All right. Do I have a formula for work? What is it? Force times distance. Okay. So if I'm calculating work, I'm just going to go down here, and then I'm going to say that the force I exerted multiplied by the distance equals the final potential energy minus the initial potential energy. Do I have a formula that calculates potential energy? I do. We learned it yesterday. It's m times g times h. Okay? So really, what we're saying here is that the work I do is the result of a force exerted over a distance, and that will be equal to the final potential energy minus the initial potential energy. Now, in the example of lifting the cup from the ground to the table, what was my initial potential energy?
Zero.
Zero. Why?
Because it was at rest at the bottom.
It was at rest and at the bottom. Yeah, that's the at the bottom part is the most important part. What was its height when it was on the floor?
Zero.
Zero. Okay, its height when it's on the floor is zero. So if I go m times g times 0, what do I get? 0. That means it had no initial potential energy. Okay, and then I'd be left with this. And now the question might have given me, maybe it gave me the force and the distance and the height, which would be the same number. The distance and the height would be the same number. Okay, and it might ask me to calculate the mass or something like that. Okay, or it gives me all the other things and asks me to calculate the force. And I just a matter of manipulating them to get my solution. Everybody okay with that? Okay, so that's generally how a work energy theorem problem involving a change in potential energy would work. A work energy theorem problem involving a change in kinetic energy works very similar. All we do is substitute in the kinetic energy formula over here instead of the potential. So we would start out with work equals a change in kinetic energy. What does a change in kinetic energy look like? What is the object doing if its kinetic energy is changing? Moving, okay? And in that movement, what is it doing specifically? How is it moving?
Of course, like using your force to pick it up.
Okay, so I could be using force to pick it up, but what's happening to its velocity if there's a change in kinetic energy? It's accelerating, exactly. It's either speeding up or slowing down, one or the other, okay? Its velocity is changing. Either one of those changes, positive or negative, requires work to be done, okay? That was the slamming on the brakes to avoid hitting the kid in the street example, okay? Work was being done on your brakes by the kinetic energy of the car, okay? Does that make sense to everybody? If you're accelerating, like speeding up, okay, then the work is being done by the engine in your car and it's making the car go faster. Okay? Either one of those would involve a force acting over a distance, changing the kinetic energy of the object. Okay, so does it set up very similar to the other one? Just final minus initial. All the changes is in one case, kinetic energy is changing. In the other case, potential energy is changing. Okay? So the real challenge here is not so much the math as it is identifying what type of energy is changing. Okay? So if I've got somebody, well, let's say I've got like the Amazon person, okay? They arrive at the bottom of an apartment building and they have to deliver a package to the 10th floor. Okay? So they go and they walk up the stairs because there's no working elevator because that's the way my question's working. Okay? And they walk up the stairs, their velocity is constant all the way up the stairs. When they get to the 10th floor, have they done work on the box? They have, because they've changed its what kind of energy? It's potential energy. It isn't moving any faster than it was at the bottom of the stairs. In fact, it's probably stationary bottom and top. Okay? But when they get to the top, it's now much higher than it was when they were at the bottom. Okay? That would be a change in potential energy, and I would set the question up like this. Okay? If there was a really angry person who didn't want the package, and they throw it at the Amazon person, this is getting really weird, but okay, then that would involve a change in the kinetic energy of the box because it would go from rest to whatever velocity they throw it at. Okay? That would be changing the kinetic energy of the box. Okay? It's work in either case. It's just what kind of energy are you changing? You have to be able to identify that based on is its height changing or its speed changing. If its height is changing, it's a change in potential. If its speed is changing, it's a change in kinetic. Is that pretty clear? That's how you identify. Okay? All right. So let's look at a roller coaster example. So if I'm down here, most roller coasters start at the bottom, okay, and they're towed up the first hill, okay, to, well, the highest point. That would be a weird roller coaster, but okay, say up to here. Okay? They're towed to that first point, and then they go down from there. Does that require work? Okay. When they're towing them up to the top, is their velocity pretty constant? Okay, so what kind of energy are they changing about the roller coaster when they're towing it to the highest point?
Total weight of everyone on the coaster?
Well, they wouldn't be changing their weight. What kind of energy would they be changing? Their potential energy. Because they're going to go from here to here. I mean, unless everybody craps themselves in the roller coaster, their weight's not going to change. Okay, and even if they do, it's all still in the roller coaster, so the whole system's mass isn't going to change. Right? That's really disgusting, but yeah, I mean, I'm just trying to validate that yes, if the mass changed, the energy would change as well. Okay, all right. So once I get to the top, to that highest point, now the thing starts to fly down the track. What does the potential energy turn into? Kinetic, exactly. Okay, it's a mechanical energy conversion. That's not work though. okay? It's not work because the total mechanical energy isn't going to change. It's just going to convert from potential into kinetic. And so the amount of energy won't change, okay? So unless the amount of energy changes, there's no work being done, okay? That's what we call conservation of energy, which is what I'm going to talk about next week. All right. Right, so mechanical kinetic energy, okay, we've already said, is calculated by going 1/2 mv squared. So we take 1/2 times the mass times the speed squared, and we'll get the kinetic energy of the object. Now, that's still going to calculate joules, okay? Remember yesterday we talked about how a joule is a kilogram meter squared per second squared. Okay, what are the units for mass?
Kilograms.
Kilograms. Okay, and what's the units for velocity? Meters per second. But velocity is squared, so I'm going to have kilograms times meters squared per second squared. Well, that's a joule. Okay, so I'm still going to get the same units, even though I'm multiplying different things together. Okay. All right, I want you guys to copy this one down. This is going to be our first example of a work energy theorem problem. Okay, so I'll give you a minute here to get it copied down, and then we'll go over it together. Okay, so like any other problem that we've done in this course, the first thing I want to write down are my givens, because I need to be able to identify what kind of question this is. Is it a V equals D over T question? Is it an acceleration question? Is it a work energy theorem question? Is it a conservation of energy question? Because there's all different kinds of problems, but they have different sets of givens. Okay? So in this one here, it says a rubber band is stretched 0.85 meters. That's a decimal there. So it's not 85 meters, it's 0.85 meters. What does meters measure? Distance. Okay, so they gave me a distance. Okay, by a force of 60 newtons. What did they give me there? Force, exactly. The things I'm going to use to get that, yes. Okay, force. They gave me force, 60 newtons. Okay, at what speed would it propel a 0.125 kilogram ball? Okay, kilograms measures mass, so I've got a mass in there. And I'm looking for the speed it would reach. So that would imply there's a change in speed, and that I'd be looking for VF. Okay, now from the context of this question, if I put something in a rubber band and stretch it like this, what's its initial speed? How fast is it going right now in my imaginary hands? Well, my hands aren't imaginary. The imaginary ball and rubber band. Zero. Okay, so that means its initial velocity then, or speed, sorry, not velocity, is 0 meters per second. All right. Sometimes my givens come from the context, not from actually being told. All right, and that's kind of the tricky part for work energy theorem questions. All right, so I've got force and distance, which I can use to calculate work. Agreed? All right, and I'm being told that there's a change in speed. So what kind of energy is likely changing in this question?
Kinetic.
Kinetic. There's no mention of it going higher or lower. All right, so this question is a work energy theorem question where kinetic energy is being changed. Okay? Make sure you're writing down what I'm doing here, okay? Because this is your first example of a work energy theorem problem, and I had a question just like this on the final exam last year. Okay? And this is the first one we're doing, which means it's like one of the most basic ones. Okay? All right, so work is a change in kinetic energy, and I want to find VF. So do I have a formula that calculates work? What is it? What?
Force and distance.
Force times distance. Okay, how do I calculate change in kinetic energy? Change always means something minus something. What are the somethings?
Final velocity minus initial velocity.
Okay, it's going to be final something minus initial something, but it's not just velocity, it's going to be the change in kinetic energy, so it's going to be the final,
half mv squared.
right, it's going to be the final kinetic energy. I'm actually not going to get there quite yet, but yes, you're absolutely right. The final kinetic energy minus the initial kinetic energy. Make sure you write down every step I'm doing here, guys, because you're going to want to have an example. Okay? All right. I have a formula for kinetic energy. Julianne just told me what it was. It's 1/2 mv squared. But before I do that, can I simplify this equation a little bit? Is there something I can take out of that equation right now?
The initial.
Right. Why can I take the initial kinetic energy out of that equation?
Because it's 0.
Because it's 0. Remember, when I'm holding the ball in the rubber band, it has no energy yet. The rubber band has energy in it, potential energy, elastic potential energy, but the ball doesn't. Okay, so this is 0. All right, now I have less to write. Okay, so now I'm going to write that force times distance equals the final kinetic energy. Okay, do I have all but one of those variables? I have force, I have distance, I have mass. The only thing I don't have is the final speed, and that's what the question wanted me to calculate. So now, it's just a matter of algebra. I want to get VF by itself. What do I do with the half and the m?
You divide them.
I divide them over to the other side, right? Everything's being multiplied here, so okay, that calculates VF squared. I only want VF. How do I get just VF? Square rooted. Okay, if VF is squared here, and I square root both sides, the square root of VF squared is VF. Okay, can I plug that into my calculator? Okay, now some people like to do this like all in one operation. I wouldn't suggest that. I don't even try and do that all in one operation. What I mean is try to do it this way. They're like, okay, I'm going to take the square root of, and then I'm going to put brackets, and I'm going to do all this stuff. Inevitably, you mess up the brackets somewhere and you get the question wrong. So what I do with this is I simply go, all right, here are my numbers. Okay, sorry, I haven't plugged the numbers in yet. Okay, so my numbers are 60 newtons, that's the force, okay, times the distance, 0.85 meters, divided by 1/2 times 0.125. Okay, so now I'm going to go 60 times 0.85, and then I'm going to divide that by half of 0.125. That I have to put in brackets. Okay, I have to make sure it's actually dividing by the full number. And then I'm going to square root that number. Okay, is that ball really moving? I wouldn't want to be in front of that. Okay, it's moving at 95 meters per second. That's fast. Okay, that would hurt. That's why slingshots are, dangerous. You could take your eye out, truthfully. All right, so our final speed then is 95 meters per second because we did work stretching back the rubber band. When we let it go, the rubber band did work on the ball and changed its kinetic energy from 0 to another value. That value corresponds to a speed of 95 meters per second. Okay, everyone kind of follow how that worked? Okay, here's the good news. All work energy theorem problems basically work the same way. Okay? All that changes is, are you looking for V, are you looking for F, or are you looking for D? Okay, that's really what it would come down to. Or if it was a potential energy problem, are you looking for H? Okay, so they all have a similar set of steps. We write down our givens. That'd be step 1. Okay, we identify what kind of energy is changing. That would be step 2. We set up work energy theorem. That would be step 3. Okay? We manipulate. That would be step 4. We plug in and solve. That would be step 5. Okay? But it's always the same set of steps. Okay. All right. Questions there? Anybody still need that up? All right. I want you guys to try this one. Okay, so we have a tractor pushing a rock. The mass of the rock is 550 kilograms. It pushes it from rest to a speed of 4 meters per second over a distance of 25 meters. What force was used to do this? Okay, so write that one down and then give it a try. Okay, so first thing we got to do, write down our givens. Okay, so in this question, our givens are the mass of the rock, 550 kilograms. Okay, we know that it goes from rest. What's that? It's our initial velocity, and it's 0. So what does that mean from a kinetic energy perspective? Does it have any kinetic energy initially? It doesn't. Okay. And it says it accelerates to 4 meters per second. Okay? And it does that over a distance of 25 meters. What force was exerted? Okay, so if I'm looking at my givens, I've got VI and VF. Okay, but I've also got distance and mass, so this is definitely not an acceleration problem. I wouldn't use A equals VF minus VI over T for this because I don't have the stuff for that. Okay, but what I do have are distance, VI, VF, mass, and I'm looking for force. Okay, there's a change in energy going on here. It's going from 0 to 4 meters per second, which is a change in kinetic energy. So that's my second step. This is a work energy theorem question. And in this particular case, it's a change in kinetic energy. All right. Next step, I need to expand this statement out. The way I calculate work, force times distance. That gives me a way to calculate what the question is looking for, which is force. Okay? If you didn't have this done already, make sure you're writing down what I'm doing. Okay, and then change in energy is going to look like this. My final kinetic energy minus my initial kinetic energy. But as we were saying before, since it starts from rest, my initial kinetic energy is 0. Okay. So now I can expand this out another bit. Okay, I'm going to say force times distance equals 1/2 times the mass times the final speed squared. Okay, what do I do next? I'm looking for force.
Divide by D.
Right, divide both sides by D. I want to isolate force. Okay, now I can plug in my numbers and solve. Right, so force is going to equal 1/2 times 550 kilograms, the mass of the rock, times 4 meters per second. But that number is squared because b is squared in the formula. Okay, divided by 25 meters, the distance over which the tractor accelerated the rock. Okay, so that tractor used 176 newtons worth of force. Okay, how many marks would a question like that be out of?
5.
I'd say 5, maybe 6. Okay, 1 mark for your givens, 1 mark for identifying it as a work energy theorem question where kinetic energy changes, 1 mark for setting up work energy theorem, 1 mark for your manipulation. Sometimes I give a mark for plugging in the numbers, that would be 5, and then this would be 6, or I maybe wouldn't and it would be out of 5. So it would be 5 or 6 marks, okay, for that question. Okay, were those steps very similar to the steps in the first question? Okay. The only thing that changed was instead of looking for VF, we were looking for F instead. Okay, so they work on a pattern. Once you learn the pattern, okay, work energy theorem problems are pretty straightforward. Okay, I know they kind of seem like a lot right now, okay, but as long as we understand what goes on in a question, we can figure out what kind of energy is changing and then go to the pattern. Okay, let's try this one and then I'll give you guys a little break. So write that one down and give it a try. Okay, so in this one we got a 10 kilogram package, so they tell us the mass. Okay, it's picked up on the 3rd floor of a building, 30 meters above the ground. What is that telling me? It's telling me a height. Is that the initial height or the final height? It's the initial height because that's where it was picked up. Okay, so my initial height would be 30 meters, and they're taking it to the 10th floor, where the final height will be 100 meters. Okay, and they're wanting to know how much work is being done. Okay, so if they tell me you need to calculate how much work is being done, is this definitely a work energy theorem question? Yes. Okay, sometimes questions are nice that way, and they just tell us, here's what kind of question I am. Okay, so in this case then, I know that work is being done. What kind of energy is that work changing? Somebody go first. The potential. How do I know that? What's changing? The height. Okay, anytime there's a change in height, then we're changing the potential energy. There are no speeds given here. Okay, so that means that there's no change in kinetic energy in this question, just a change in potential energy. Okay, so that's going to mean the final potential energy minus the initial potential energy. Okay, how do I calculate potential energy? What's the formula for that? Adam, what's the formula for potential energy? Okay, who doesn't? Who can tell?
MGH.
MGH. Okay, so the work being done here is going to be the final potential energy, which is M times G times the final height, minus M times G times the initial height. Okay, that should calculate the change in the potential energy of the package. Okay. So all I have to do now is plug in my numbers. I don't have to worry about force times distance. I wasn't told the force. I kind of know the distance, it's 70 meters, but it doesn't matter because that's not what I'm being asked to find. Okay? I'm just going to put in here that it's 10 kilograms times 9.81 times 100 meters minus 10 times 9.81 times 30 meters. Okay. that I can punch directly into my calculator exactly as it appears there because it'll do order of operations correctly. Okay, so that's going to require 6,867 joules worth of work. Okay, and if you're like really sharp with math, you might have figured out that you could also do this 10 times 9.81 times 70. Right, all it was changing was the height, M and G were staying the same. Doesn't work for kinetic because you got a squared in there, but okay, it does work for potential. So the work being done was 6,867 joules. Okay, all right, let me give you guys a break here. It's 9:26, so I'll give you a break till 9:30, and then we'll get started on another one. Okay, I'd like you guys to try this one. The answer is there. It's 3.16 meters per second, so you'll know if you did it right or not. Okay, so I'd like you to try this one about the bulldozer. They tell you the work in this one, which actually makes it, again, easier than the first two that we did. Okay, because there's kind of one less calculation here. So they're telling you the work. They're going from a speed of 2 to an unknown velocity. Okay, the truck has a mass of 2,500 kilograms, so you're looking for its final, well, speed really, it's not really velocity. Okay, give that one a try. I'll give you some time on that. All right, so our givens are in this question, we know the work, 75.
Lost the wording. Oh.
So good. It does a weird thing now. Yeah. Okay, 7,500 joules. Okay, and it's pushing a truck from a speed of 2 meters per second, so that would be my initial speed, to an unknown velocity. So VF is probably what I'm looking for. Okay, the truck has a mass of 2,500 kilograms. All right, so there's my givens. What kind of energy is changing in this question? Kinetic. Speed's changing. So this is a kinetic. There's no mention of it going uphill or anything like that. So there's no change in potential here. The work being done is changing the kinetic energy. All right. So I already know the work. So I don't even have to put in the force times distance part. I know what this number is already. Right? So I'm just going to say that change in kinetic energy is EK final minus EK initial. Now, what I'm looking for is the final speed. That's part of the final kinetic energy. Agreed? So can I move the initial kinetic energy over to the other side right now before I put a bunch of letters in and confuse myself? I can. Okay? And it's probably not a bad idea to do it now than before I have the 1/2 mv squareds in there. Okay? So right now I'm going to take work, which is a change in energy, and I'm going to add the initial energy to the change. That should give me the final energy, agreed? Okay, so I'm going to add EK initial to both sides, so I'm going to end up with this, work plus EK initial equals EK final. All right, now I'm going to expand that out a little bit more. Okay, I'm going to say that work equals, or sorry, not equals, work plus 1/2 times mass times VI squared equals 1/2 times mass times VF squared. Okay, everybody okay with what I've done there? Okay, so I've moved the initial kinetic energy over before I plugged in the numbers. If you moved it over after you plugged in the numbers, that's fine too. It doesn't change that you're allowed to do that. Okay? Now what I'm looking for is VF. So what do I have to do with the 1/2 and the M to get rid of them? Divide them over to the other side. Okay, that gets me VF squared. What do I want? I don't want it to be squared, I want it to be normal, so I need to
Square root.
square root. Okay, so it's a bit of a trickier manipulation, okay? But in the end, it's algebra, okay? So I'm gonna plug in my numbers, 7,500 plus 1/2 times 2,500, the mass of the truck, okay? Times 2 squared, the initial speed of the truck, divided by 1/2 times 2,500. Did I mess something up somewhere? Feel like I did. Oh, I subtracted. That's where I messed up. Okay, sorry. I messed up a calculation up top, guys. Hang on, we'll start that over. 7,500 plus 0.5 times 2,500 times 4. That's better. Okay, and then divide that by 0.5 times 2,500. And then square root that. That'll be 3.16. Okay? All right, everybody okay with that? Easy to make a mistake on your calculator? Happens to me all the time, okay? That's when you gotta be able to look at the question and go, wait a minute, how come my answer's smaller when it says it's speeding up? That doesn't make any sense, and then look back at your work and go, oh, because I subtracted instead of added somewhere. Okay, that happens sometimes. All right, so we get 3.16 meters per second as our final speed. Okay, was it still the same pattern? I wrote down my givens. I identified the type of energy that was changing. I set up work energy theorem. I manipulated and solved. Still the same steps. Okay, that manipulate and solve part changes each time, but the steps are still the same. Okay, questions on that one? All right, so this is just the pattern stuff that I was talking about before. So if you're solving any work energy theorem question, okay, first thing is, write out your givens, okay? Then identify the type of energy being changed. Is it potential or is it kinetic? Okay, how do you tell? You look for a change in height or a change in speed. Okay, if it's a change in height, it's potential. If it's a change in speed, it's kinetic. Okay, then you set up work energy theorem, so work's a change in energy, okay, and we would set up EF minus EI, okay, if it's kinetic, then it would look like this, 1/2 MVF minus 1/2 MVI. If it's potential, it would look like this, MGHF minus MGHI, and then we would manipulate and solve, okay, as our final step. Okay, that's the pattern. The pattern's always the same. The biggest trick is figuring out which type of energy is changing and what you're looking for. I don't like that one. Okay, try this one. So we got an inclined plane, it looks like this. Okay, we're pushing the box up a 25-meter long ramp. Okay, we know the force is 150 newtons. Okay, we're looking for how much higher it will be at the top of the hill. Okay, all right, give you a few minutes on that one. Okay, so in this one, we're told the mass. Okay, so we know the mass is 35 kilograms. We know the force being used is 150 newtons. We know the distance that it's being pushed is 25 meters. Okay, and we're talking about the bottom of the hill and the top of the hill. What's my height at the bottom of the hill? 0. Okay, so I know my initial height is 0 meters, and I'm looking for the final height of the box. That is how much higher it is when it's at the top of the hill. Okay, looking at my givens and the context of the question, something being pushed up a hill at a constant speed, what kind of energy is changing in this question? Potential energy is changing, okay? The height's changing, the speed isn't, right? So that means that my next setup then is that in this question, work is a change in potential energy, right? Now, they give me the force and the distance, so I know I'm going to have to use that, force times distance, and I know there's a change in the potential energy, so that's going to be m times g times h final minus m times g times h initial, which we already established is how much? 0. Okay, can I solve for the final height? All right, what do I do with the m and the g? I want to get hf by itself. What do I do with m and g? Divide it over the other side. All right, so that's going to get me hf. So when I plug in my numbers, that's going to be 150 newtons times 25 meters. That's the length of the ramp. Okay, divided by 35 kilograms, the mass of the box, times 9.81. That's g. Right, that'll give me the final height at the top of the ramp. So 150 times 25, okay, divided by 35 times 9.81. That does have to be in brackets, otherwise your calculator will do it in order, which you don't want. All right, so it's 10.9 meters higher, or the ramp is 10.9 meters tall. Did that one follow the pattern exactly? It did. Okay, and was probably a little easier context-wise than maybe some of the other ones have been. Okay, all right, we've been working pretty hard today, so we'll say in your last 5 minutes here, okay, you can have a look over a few things because your unit exam is coming up on the 20th. Maybe you look over some B equals D over T stuff or something like that.